Hello everyone, this is Rod Sidwell. We're going to talk about activity 9-1 in this video, hydraulic systems. And I kind of want to review a couple other concepts as we go along. Let's look at this homework problem. A hydraulic system has a force applied to a small piston. Hydraulic liquid transmits the force to a large piston over here. The large piston applies the magnified force in the desired application, that's this. To increase the effectiveness of the hydraulic system, a mechanical arm can be added to multiply the force. And here's the mechanical arm. So we're going to first talk about the liquid. Now, liquids are incompressible and they flow, so they're going to exert the same pressure everywhere, not counting the hydrostatic head. And so if I have 10 pounds per square inch pressure in the liquid here, then the pressure here is 10 pounds per square inch, the pressure here is 10 pounds per square inch, pressure here is 10 pounds per square inch. So we know that the pressure is equal to a force divided by an area. And we can, if we know the area of these pistons, we can readily and easily find the forces involved. The pressure in this cylinder is the same as the pressure in this cylinder. I could say P1 equals P2, and that's just like saying force 1 over area 1 is equal to force 2 over area 2. So all I really need to know is the difference in areas. So force, the upward force, force 1 would be equal to A1 over A2 times force 2. So this is the downward force. This is the upward force, and here's the ratio of the areas. So if this is 1 square inch and this is 10 square inches, the force is going to get magnified by a factor of 10. Now the other thing the book doesn't really talk about that's going to make this problem easier to solve is the concept of torque. So let's talk about that. So if I have a point which has a lever, and this lever can rotate about this point, so it's fixed at this end and it's free to move on this end. So that's going to be like this. Okay. Now, if I put a force of 1 pound down here, and this is 1 foot long, then that's going to tend to rotate clockwise. That's the definition of 1 foot-pound of torque, is 1 pound at 1 foot. If I had a 10-foot long beam, and put that same pound on there, now I have 10 foot-pounds of torque. So you're familiar with this, everybody's familiar with the idea of if you can't get a bolt or something undone and you go and reach for a longer lever arm or a breaker bar or a wrench that has a bigger extension. Now in this problem here, the way to think of this lever arm is to say, you know, I have to balance the forces. So here's my, let's just look at this lever arm here. So I've got really two places I'm putting force on this lever arm. One where I'm putting F sub L on, out here at the end, and then another one where there's a countering force from this piston. So they're showing it as, you know, if I put a force down here, that's the same as putting a force down here. The other way to look at it is, I'm pushing down on this end. The pressure on this piston from the other side has to be able to hold up this beam to keep it from moving around. So this force has to balance this force. Now, if this beam were 2 feet long, this is out here at 2 feet, and I put a 1 pound force on there, now I have 2 foot-pounds. And we could write the symbol for torque if we want to, equals, and it's just a Greek letter tau, F times L. So for this to not move, I need a counter force of we've got 2 times 2 feet, 1 pound, 2 foot-pounds. So I need a 2 foot-pound torque to rotating the other way to make this balance. So if this were at 1 foot out, if this is 1 foot out from here, 1 foot right there, then this would be applying a force of 2 in the other direction. So really all you need to know to deal with these lever arms is just the ratio of the lengths. So the mechanical advantage is just big L over little l. And if you look on here, let's zoom in. You can't really see it otherwise. Okay, here's big L, here's little l. If little l's 1/2 big L, then whatever force is here gets multiplied by a factor of 2 by the time it gets over here. Now they tell us what L is in some of these problems. So that's a good way to look at those, is to think of it as a force balance. You have to figure out how much force do I need to keep the thing from moving. What is the working force F? That's the working force up here. In pounds, when the force applied to the small piston F is 20 pounds, small f equals 20 pounds. So that's this right here. The area of the piston is, and they give us the number, 0.1963 square inches, and the area of the large piston is 3.14 square inches. So just like we looked at a little while ago, big F is going to be equal to the ratio of areas. And we can just prove this to ourselves. Okay, the pressure here, let's just write it again, I guess. Okay, I'm going to call this P sub L for P large, for the large piston. It's equal to the P sub L of the small piston. So this pressure in here has to be the same as the pressure over here. So if I write that, for this piston I get F, this is in the big F, divided by the big area, which is 3.14 square inches. And if I write it for the small piston, I know what F is because they tell me, 20 pounds. And the area is 0.1963 inches squared. Oh, there we go. You couldn't see it. Alright, so just like with any equation, what I want to do is I want to take all my knowns on one side and leave my unknown on the other side, and I do that, I'm going to have F equals 3.14 over 0.1963 times 20. And that's going to be, and the units are going to work out to be pounds, because the inches, square inches, and square inches are going to cancel. And I get F equals 320. Okay, on to number 2. Number 2 says, what is the force applied to the small piston F, right there, in pounds, that is required to deliver a working force of 1,000 pounds over here? The area of the small piston A is 0.1963 square inches, and the area of the large piston A is 6.28 square inches. Okay, so we're just going to go back to that one thing we know over and over again. Pressure large equals pressure small. And now let's write out what we know. So F of large, so that's going to be F of large over area of the large, P sub large, equals 1,000 pounds, because they're asking about that. They tell us the area, 6.28 inches squared, and that's going to be equal to the pressure on the other side. And what do we know? We don't know the force, but we do know the area, 0.1963. So the force, if I rearrange this, is going to be equal to 0.1963 divided by 6.28, and the number I get is 31.2 1.258. All right, so let's see, and I rounded that. I have a longer there. What is the working force F in pounds when the force applied to the small piston F is 25 pounds? The area of the small piston A is 0.0491, and the area of the large piston is 12. Well, that's going to be a huge magnification, and we expect a very large force. And when I take 12.56 and divide it by this number, and then multiply by 25, I'm going to get 63.95. Okay, so on to the questions about the handle. A handle is added to increase the force available to apply to the small piston. The length of the mechanical arm, L, is 18 inches. From the pivot point to the point where the force is applied. The length of the mechanical arm, little l, is 1.25 inches. So if I just take the length of the big arm divided by the length of the little arm, that's 18 divided by 1.25. That's the mechanical advantage. So if you know one force, you can use this mechanical advantage to find the other one. And I get 14.4. What is the working force F in pounds when the force applied to the mechanical arm is 20 pounds, the area of the small piston? Okay, so now what we're going to have to do is it just becomes a two-stage process. We have two multiplying factors. So we're going to put 20 pounds out here, and as I do that, this force here is going to be much higher because this lever arm is small. In fact, it's going to be 14.4 times higher. So 14.4 times 20, that's going to give us little f. And now I can use little f to find the pressure in here. Then I'll know the pressure over here. But we've done this many, many times. It's really just going to be the ratio of the areas, but we can just go ahead and do it the long way. I'm going to first find the pressure in the small chamber. I'll just call it P sub S. And that's going to be equal to little f divided by the area, which is 0.1963, and little f is equal to F sub L, that's this force here, times our mechanical advantage, 14.4. Get my calculator here. So 14.4 times, what did they say F sub L was? 20 pounds? Okay. So 288 pounds of force. And that's just like saying 288 pounds versus 20 pounds. And here's my lever arm. So this gives a counterclockwise torque, and this gives a clockwise torque, and they balance. And they balance because this lever arm is 14.4 times longer than this lever arm here. Okay, so we've got F, so now we can find the pressure in the small solenoid. It's 288 over 0.1963. But we also know that that's equal to the pressure in the large cylinder. And the pressure in the large cylinder is equal to the force, that's what we're after, divided by the area, which is 3.14. So we can rearrange this. Let's just do that. F equals, I'm just going to multiply 3.14 over 0.1963. Now there's the hydraulic advantage owing to the different areas of those two pistons times 288, and that'll give us an answer of 4606.8 pounds. And one other way to look at this is to say I've got both a hydraulic advantage and a mechanical advantage. So I could just write these as I could write the area of the large over the area of the small piston, and then I could have the lever arm, let's call it, what do we want to call it? We'll just call it L, that's what they call it. Big L over little l, all times 20. If we did it all at once, that's what it would look like. All right, that's the end of activity 9-1.